Hi everyone, Daniel Bogdanoff here. In my last 2-minute Guru episode, somebody with a sharp eye noticed a little glitch on the waveform, and if we zoom in using that same circuit, we definitely see there is a little bit of a glitch there, and it actually makes itself more prevalent at higher frequencies. So if I crank that up, we can see that there's a glitch both on the rising edge and the falling edge of this simple capacitive circuit. And we were able to narrow this down to some simple parasitic inductance in my circuit. So I thought today we'd look at how we narrowed that down and what's actually happening to cause this glitch in the system. And my setup is pretty straightforward. Here I have a square wave coming out of my WaveGen to these little clip leads. I have that on a wire going into a breadboard and a capacitor between the two, and I'm probing the positive and negative sides of those different rails. Now, if you've prototyped with breadboards before, you know you're already set up for some issues here because inductance and capacitance is in everything, and breadboards and these jumper leads are notorious for having unwanted capacitive and inductive effects. This glitch is a side effect of how capacitance and inductance, and likewise capacitors and inductors, respond to an AC step response. So let's pull out the whiteboard and look at the step response of inductors and capacitors, and look at the effective circuit that I have here, not just a single capacitor. So we're going to look at 3 different things. This is going to be our voltage source, and that's just going to be a step function up. So it starts at 0, and at time t equals 0, it's just going to be a step function straight through. The next thing we're going to look at is a capacitor, and we're going to measure the voltage across a capacitor if we're applying this V source. So obviously at 0, there's nothing. As soon as this steps on, the voltage across the capacitor is going to act as a short. So effectively at t equals 0, my capacitor looks like a short from this node to this node. So it's going to be 0 volts. And then as time goes on, this capacitor is going to essentially charge up with respect to its time constant. And at some point out here in time, maybe t prime, it's going to hit that same voltage source. So it's going to be the same. And at this point, if the voltage across this capacitor is the same as the voltage source, this value is going to be V+, and now it's going to look like an open circuit. And next, let's look at an inductor, and we draw it with this little squiggly line here. And we're going to look at the voltage across the inductor as we get a step response from our voltage. And an inductor is essentially the opposite of a capacitor. So it's going to start actually as an open circuit. It's going to resist a change in current. So at time t equals 0, we still have 0. But as soon as the step turns on, we're going to get pretty much a spike right up to V+. And over time, that's going to decrease down to be about 0 volts. So here at T0, the inductor looks like an open circuit, and at T1, the inductor looks pretty much just like a wire. It's fully charged up, and everything can move through it as if it was a wire. And now the bigger your capacitor, the longer it's going to take for it to charge up to that V+. And likewise, the bigger the inductor, the longer it's going to take to settle down to the voltage applied to it. And if you take a smaller capacitor, it's going to charge up faster. And if you take a smaller inductor, it's going to discharge much, much slower. So keeping all that in mind, let's map out the effective circuit that we had. So first we have our WaveGen, and we're going to treat this as pretty much an ideal waveform generator. And it's going to provide us a step function in the form of a square wave. That's going to go up here, and since it has a 50 ohm output, there's a 50 ohm resistor here. That's not really going to play into this too much. Then we have those wires, which are going to have an inherent inductance. And we go down to our capacitor, and there's going to be another negligible inductance here from the other wire, and that's going to go back to ground. So here we have a full circuit path. And we're probing here at the output of the function generator and here at ground. So let's look what happens when the WaveGen is going from low to high. This is going to become an open circuit. This is going to become a short circuit. This is going to become an open circuit at that instant that the WaveGen goes from low to high. And if I'm measuring from this point to this point, effectively, I'm just measuring the output of the waveform generator. So I'm going to see instantly a big spike on my oscilloscope. But since the inductance from my wire is so small, this is going to go from an open circuit to a short circuit very, very quickly. My capacitor, however, is much, much bigger. I'm using a standalone capacitor instead of just modeling the inductance of my wire. This is going to go from a short circuit to an open circuit much more slowly, and that's where we start to see that long length in rise time. So if I had an ideal everything, so I had an ideal source that went from low to high infinitely fast, an ideal oscilloscope which had infinite bandwidth, it could see every frequency component, and ideal components which are appropriately modeling fully just inductance, just capacitors, etc., I would see something like this. So my waveform generator, my function gen, is going to go from low to high instantly, and this open circuit is going to kick in, so I'm starting low, and as soon at T0 here, as soon as that kicks in, I'm going to drop my signal high, and that inductor is going to start to charge up, and it's going to drop down pretty fast. At the same time, my capacitor is kind of over here charging up and doing this, waveform, soft edge that we know about. So once my inductor discharges enough, at the same time, my capacitor is going to start to charge up, and my circuit's going to look something like that on the oscilloscope. So I'll see a spike, and that's going to be the same voltage, ideally, as the waveform generator, and it's going to drop down. The capacitor is then going to start charging up and start to look like a short circuit because my capacitor is so much bigger than my inductor. And when we go from high to low, it's going to be essentially the exact same thing. This is still going to act as an open circuit. This is going to act as a short circuit, and here we're going to have another open circuit. And if I probe from here to here, again, I'm still just measuring the output of the waveform generator, which is now low. So let's again go back to our ideal world. Here my voltage is stepping down. It's the falling edge of my waveform generator. And at that time, t equals 0, my inductor is open. It's acting as an open circuit. So I'm going to see my actual voltage go straight down to 0 because it's ideal, and then that inductor is going to start to charge up super fast because it's a really small inductor, and at the same time I have my capacitor starting to discharge here, so my voltage over time is going to be this drop down to 0 volts because of my ideal inductor, and as soon as that inductor charges up, my capacitor is going to kick in and start discharging, and I'm going to get down to V minus here, which is at the bottom from V plus. You'll also notice I didn't really talk about this inductor here. That's because it's on the back side of a capacitor, so it's not going to see any sharp edges like this inductor is seeing. The capacitor is going to filter that edge into something smoother, and for modeling purposes, in this case, we can effectively consider that to be a short circuit, pretend it doesn't exist. So let's go back to our circuit in the oscilloscope. So you can see all these wires are that inductance we modeled on the whiteboard. I'm going to drop the frequency down a little bit so we can look at this a little more clearly. We can still see that I have a glitch on the screen. I also want to point out real quick, there's a formula that lets you calculate the inductance of a wire based on its length and width. That formula is here. So you don't actually have to have a wire in a coil for it to have inductance. In the 2-minute guru video, I had a resistor in parallel with my capacitor, and we were able to identify that this was the source of inductance by measuring just this resistor, which was effectively a way for us to measure the capacitor alone. So let's go ahead and move that over and see what we get. And you can see when I'm measuring just my resistor, I'm not getting that spike anymore. Even if I zoom in, you can see there's a tiny little spike, but that's really not much of anything at all compared to the spike that we're seeing when I connect to this. So you can see the difference when I'm connected here versus connected to the resistor. So that was our clue that the wires were causing the inductance. So let's get rid of this resistor again, and let's remove these wires and just connect to the capacitor from the WaveGen. Now technically there's still going to be some capacitance in these wires and in the probe and some inductance also. That's just the nature of electronics as a whole. But that's something that I think we can drop out pretty significantly. So let's go ahead and grab the capacitor and ground it also, because if I don't ground it, I'm going to still have this inductance in my ground path from the WaveGen. I'm going to have to hold that on there and get my ground connected. And sure enough, our inductive spike goes away. I'm going to zoom in on that using my oscilloscope, and you can see if I look really, really closely, get really sensitive, there's a little spike there. But overall, my spike is gone because I've gotten rid of all the parasitic inductance. And you can see that spike is pretty good if I stay at that 200 millivolt per division setting and go back to my old setup. Now you might ask, why is the spike only, it looks about a volt tall instead of the WaveGen, which is a 5 volt peak-to-peak signal. So I'm only getting 20% of my maximum height. That's because the scope is not ideal and the WaveGen is not an ideal system. So if I had an ideal edge, this might go higher, but the scope's bandwidth is not going to be fast enough to go to measure the pulse all the way to the top and all the way to the bottom of that 5 volts. And even if my scope was ideal, my WaveGen, my function generator, there's no such thing as an ideal one. So its rising edge is not going to be fast enough to get you there to that 5 volt max in that amount of time. And we can also make that glitch even bigger by adding our own inductor in series with our circuit. So I've added an inductor in series with our circuit here. The red wire is a bypass, so that's what we've been seeing on our circuit. The black wire puts that inductor in series. So as soon as I pull out the red wire, we can see a pretty significant spike from this extra inductance. So that shows that the spike is caused by inductance in series with our circuit. So ultimately what this means is you have to be very, very careful in your systems and your electronic circuits to make sure that you're not using crazy long ground wires, or if you're going around and using an oscilloscope, especially a very high bandwidth oscilloscope using some high bandwidth active probes, having a long ground lead like this is going to put too much inductance into your measurement. You want to use those little ground spring clips that come with your probe. I'll go grab one and hold it up. Here's the little ground spring thing. You can take your probe, pop the hat off, and then turn this around and kind of squeeze it down onto that probe ring. And then once that's all the way on there, you have a little ground point and you can get a very clean ground and a very clean measurement on your signal. So long story short, be careful with your boards, be careful with your circuits, make sure your test jigs aren't having long leads like this, and make sure your testing is done with a very good, clean ground and a good probe connection, because things like this can cause you trouble down the road. That's all for today. If you liked this style of video, let me know, give me a thumbs up, put it in the comments, and if you haven't already, make sure you subscribe to the Keysight Oscilloscopes YouTube channel. I'm Daniel Bagdanoff. I'll be back next time with a 2-minute guru video on inductance. Oh, you can't see that at all, can you?